I mentioned in a previous video that waves carry energy and momentum. In this video, we'll discuss in more detail how sound waves transport energy from one object to another. To have this discussion, let's first define power and intensity. Whether we're talking about sound or light or some other type of energy, these terms deal with the transmission of energy from one object to another. Say the source of the energy is here and the object receiving the energy is here. Conceptually, you can picture a packet of energy, delta E, being transferred from the source to the object like this. When discussing light or sound, this energy is often transferred continuously, so you can picture a stream of energy packets being transferred from the source to the object like this. The rate that these energy packets are being transferred is the term power. The equation for power, then, is energy divided by time, where delta E is the amount of energy transferred in time delta t. Notice that because the calculation is done over a period of time, the mathematical result is average power over that period of time. And as we already know, the SI unit for power is a watt, which is a joule per second. So back to the picture we were just discussing. When energy is transferred continuously like this, we often refer to the power of the source and the power of the object receiving the energy. In the case of sound, the waves usually propagate spherically away from the source. So if this is the source, we can picture a packet of energy radiating away from the source more like this. As you can see, the packet of energy is spreading out over a larger and larger area. And if the source continuously emits this energy, it looks something like this. Again, the packets of energy emitted by the source are spread out over a larger and larger area, like a red balloon that's being blown up, and the red color becomes less and less intense as the balloon gets larger and larger. Notice if the object receiving this sound power is here, then it only receives a portion of the total power emitted by the source. The term intensity refers to how much the emitted power is spread out over an area such as this. So we define intensity as the emitted power per area. The equation for intensity, then, is the emitted power divided by the area over which that power is distributed. The SI units for intensity come from the equation and are watts per square meter. As a matter of usage, if we are discussing light, then intensity refers to brightness, and if we are discussing sound, then intensity refers to loudness. Here's an example to demonstrate the use of the equation for intensity. A speaker emits sound uniformly in all directions. Its power output is 1 watt. What is the intensity of the sound 4 meters away from the speaker? So we can start with the equation for intensity. And the critical thing to recognize is that because the sound is emitted uniformly in all directions, the waves radiate away from the speaker like ripples on a pond, but in 3 dimensions. So in a spherical shell like this. So at this distance, the power emitted by the speaker is spread over a spherical shell with a radius of 4 meters. Because of that geometry, the area in this example is the area of a sphere, which is 4 pi r squared. And then we can plug values in, and we find that the sound intensity 4 meters away from the speaker is 0.005 watts per meter squared. Now, one last thing to discuss about sound intensity. There's a practical issue dealing with the behavior of human hearing. It varies from person to person, but the useful sound intensity range for human hearing is about 1 times 10 to the minus 12 watts per meter squared to 1 watt per meter squared. Where below that range, sound is generally not audible, and above that range, sound tends to be painful and perhaps damaging to the ears. One nice aspect of human hearing is that we can discern incremental changes in the lower end of the range as well as we can at the upper end of the range. Mathematically, this is actually difficult to visualize on a traditional numbering scale. I'll show you what I mean. Here's a traditional numbering scale from 0 to 1 watt per meter squared. Say the intensity of a sound wave is 1 watt per meter squared. If the intensity drops to 1/10 of this value to 0.1 watts per meter squared, then this is clearly a large drop on this scale. On the other hand, if the intensity of a sound wave is 1 times 10 to the minus 11 watts per meter squared, it is essentially 0 on this scale. And if the intensity drops to 1/10 of that, to 1 times 10 to the minus 12 watts per meter squared, then that is also essentially 0, and the drop is too small to visualize on the scale. And yet human hearing can resolve the drop from 1 to 0.1 watts per meter squared, as well as it can resolve the drop from 1 times 10 to the minus 11 to 1 times 10 to the minus 12 watts per meter squared. So the bottom line is that we need a numbering scale that's more appropriate for human hearing. That scale is a logarithmic scale like this one. On this logarithmic scale, here's the drop from 1 to 0.1 watts per meter squared. And here's the drop from 1 times 10 to the minus 11 to 1 times 10 to the minus 12 watts per meter squared. These changes in intensity on the logarithmic scale are the same, which is how human hearing perceives it. So this is a more appropriate scale for human hearing. As a matter of practicality, the logarithmic scale is renumbered like this, where the bottom of the human hearing range, 1 times 10 to the minus 12 watts per meter squared, is defined to be 0, and then goes up by tens until the top of the human hearing range, 1 watt per meter squared, is 120. This scale is named in honor of Alexander Graham Bell, and you're probably familiar with it. It's called the decibel scale, and we use a dB as the symbol for a decibel. This scale is still intensity, but to distinguish it from intensity in watts per meter squared, we use an I for the intensity in watts per meter squared, and we use a Greek beta for intensity in decibels or dB. We often need to convert between watts per meter squared and dB because in the equation for intensity, we typically use SI units, so power is in watts and area is in meters squared, so intensity must be in watts per meter squared. On the other hand, we usually discuss sound intensity or loudness in terms of dBs because it's more appropriate for the way our hearing behaves. So here's the equation we can use to convert between dB and watts per meter squared. Beta equals 10 times the log in base 10 of I over 1 times 10 to the minus 12 watts per meter squared. When you use this equation, it's straightforward to plug in a value for I in watts per meter squared and solve for beta in dB. But you may not recall from high school algebra how to plug in a value for beta in dB and solve for I in watts per meter squared. There are a couple of worked out examples posted, and one of them goes through this process. So that brings us to the end of this video. In the next video, we'll discuss some of the interesting effects we see with sound waves.